Alright, so we are going to look at Hess's law. So Hess's law is an important concept when dealing with thermodynamics, which is just how heat moves, which is all that we've been talking about this section. So we're going to use Hess's law to figure out enthalpy change. And so we've got really three objectives for this section. I'm going to break this into two videos, but our first objective, which we're going to look at here, is using Hess's law to calculate the enthalpy change for a reaction. So by the end of this, you should be able to do that. And then also determine that enthalpy change, or the heat of a reaction, for a reaction using thermochemical equations. Now those are really similar to each other because we'll see that Hess's law tells us how to use thermochemical equations. Alright, so Hess's law can kind of be thought of as how to get from one place to another. So if I asked you to look at how could we get from Canastota School District, where we're at right now, or where I'm at, to Total Stop, what are all of the ways we could get there? Well, there's obviously the most direct route of going right down Main Street, or I could get a little bit crazy and I could come down here, Pine Street, and then to Railway and up, or I could go to the Good Sam and then up to Willow and then down Railway. All of those are viable options. Now, what happens after I take that path? Well, no matter what route I take, I'm always going to be the same distance away from where I started. So whether I go really long and I go all the way around town, or whether I go directly to Total Stop, the distance between where I started and where I ended is always the same. And that's a similar idea to Hess's law. Hess's law says that the change in enthalpy for a reaction is the same no matter how I get to it. Okay? So if I start from at A and I end up at point B, no matter whether I go directly there, just like going straight down Main Street to Total Stop, or if I take a long route there, the change in enthalpy is the same. Much like we said that no matter whether I go directly to Total Stop or I take a long detour, I'm still ending up the same distance away from where I started as if I just went straight there. Okay? So Hess's law is telling me that I could go a couple of different options there, but overall the amount of energy that's involved is the change in energy, the change in enthalpy is always the same. So we use Hess's law because sometimes some reactions happen really, really slowly, and so it's hard to accurately measure using calorimetry the amount of energy being given off. And then sometimes we have a mixture of products. So sometimes when things react with oxygen, they could form a couple of different products. And so it might be hard to know, well, how much energy was associated with making product A when it reacted with oxygen, and how much was associated with making product B. So we use Hess's law to help us figure it out in those particular instances. Okay? And so if you imagine here, what we're saying, let's put some numbers to this, that if I start at A and I go to B, let's imagine that that involves 1,000 kilojoules. Well, Hess's law says that no matter what route we take then, I'm going to always involve 1,000 kilojoules. So we said A to B is 1,000 kilojoules. Well then, if I go to A to C and then back to B, that also overall involves 1,000 kilojoules. Now it might be that it takes 100 kilojoules to go from A to C, and then another 900 kilojoules to go from C to B. But overall, the net change is still going to be that 1,000 kilojoules. And then you can imagine the same is true with A, D, E, and B. So if I go to A to D and then to E and then to B, my net change overall is still going to be 1,000 kilojoules. It could be that this going from A to D is 2,000 kilojoules, and D to E is 1,000 kilojoules, so we're at 3,000 total. Okay, but then maybe going from E to B loses 2,000 kilojoules. Okay, But so when we add all of those together, I'm still back at that 1,000 kilojoules. That's what Hess's law is saying. Okay? So I felt like this was maybe another helpful illustration of it. We start at A, we go up to B, maybe this takes in energy, and then we go to C, D, some energy there, and come back down, and overall, that change in energy is the same. So I guess that's really maybe not that different of a picture, but for me, I like the going up and coming down. It made some sense because they almost like cancel each other out. Okay, so you can also kind of think of how we use this. Think of this like building with Legos. So we have all these individual parts, and we use them to build something greater, like a Millennium Falcon, for instance, because that's awesome. Star Wars alert there. So I use these parts, and I combine them in different ways, and I might change the way that they're positioned to make this final piece. So we're going to do that same thing except with equations. So in this case, this is like my Millennium Falcon, or like my total stop. I want to get to this. This is my goal. And so these are the pieces, or like the individual Legos, or these streets that I'm going to go on to get to this end goal. So you can see already that this first equation, which is like a piece I can use to build this bigger equation, talks about ammonia, or NH3, which we want up here. And then if I look, well, there's oxygen, which is something I want in my final equation. And there's also oxygen there. I also want in my final equation to have nitrogen monoxide, which I have right here. And I want water in my final equation, which I have here. So I use these equations, and I might have to manipulate them some. I might have to move them around a little bit to make this equation. And so one of the ways that we can do that is we can flip equations, or I can multiply. Basically, I can do the equation multiple times. So if I flip, like in the instance here, if I look at my goal, my target, I want NH3 to be on the left side of the arrow. Well, if I look at this equation I'm given, it's on the right side of the arrow. So one thing I'm going to have to do is I'm going to have to flip this. I'm going to actually take this side and move it to the other side. And then these guys they trade places with each other. But also you can see that I want 4 moles of ammonia, whereas here I only have 2 moles. So I'm also going to have to multiply this to make it happen. Okay? And so that's something that we can do using thermochemical equations. And then some of the things that end up on both sides end up getting canceled out. So when I do this flipping, what happens is that if I flip, I have to do whatever I do to the reaction, I do that same thing to these numbers. So for instance, if I'm going to flip this like we talked about, I'm also going to have to flip the sign of this enthalpy change. So now, if I'm starting with NH3 and it breaks down, decomposes into these things, that's going to actually involve a absorbing of energy. So the sign is going to change. And that's what this is saying. If I flip a reaction, meaning if I swap the reactants and the places of the reactants in the products, I'm going to flip the sign of the change in enthalpy. Or if I multiply the coefficients, then I'm going to do that same multiplication to the change in enthalpy. Okay? And so you can see at this picture here, some things cancel out. What happens in using these different steps is that some things cancel out. So for instance, we've got nitrogen gas here and nitrogen gas there. So they're on opposite sides of the reaction, so they'll cancel each other out. And the same is true with the carbon. 2 carbon here, 2 carbon there, on opposite sides of the reaction, so they cancel each other out. And then I have a total of 7 hydrogen here, and 7 hydrogen on this side, so again, they all cancel out. And then what I do lastly, what I'm trying to find is the change in enthalpy. And to do that, I take all of these numbers and add them up. Okay? And this is a lot. We're going to go through some examples in just a second. And this is one example of what has been done, how they manipulated. So we flip or we reverse the reaction, we change it to positive, and then we also needed to multiply it by 2. So I took 91.8 and multiplied it by 2 to get 183.6. But let's look at an example here. So this is my target. I'm trying to get to this equation here, and these are the paths I'm going to use. These are the pieces I'm using to build this reaction. So what I do is I start with one thing, and I try to find the equation that has that piece. So in this case, I want to start with carbon. I'm going to figure out which of these equations am I going to use that talks about solid carbon. And so we can see that's the first one. So my first step is I know I'm going to use this equation right here. And in doing so, I have to write out the whole equation. Well, then I also look at the next thing that I want. Well, the next thing that I want is oxygen, and I have oxygen represented. And so let's move on to carbon dioxide. Well, carbon dioxide is a reactant, or is a product. So I'm going to look at the equation up here that has carbon dioxide and make sure that it has it as a product. And I can see that it does right there. So I use these two equations. I didn't have to flip them or multiply them, so I didn't have to change these numbers at all. So to find my change in enthalpy by using Hess's law, I'm going to, well, first off, I can see those cancel each other out because they're on both sides. And then I also see I have a half mole of oxygen here and another half mole of oxygen. So they're going to combine together to give me 1 mole of oxygen. So here I'm just rewriting everything I have that's simplified and not been canceled out. And I see on the left side of the arrow, I've only left with carbon and 1 oxygen. And on the right side of the arrow, I'm left with carbon dioxide. So to find my change in enthalpy, I add those up. Okay. So let's look at another example. And I'm actually going to skip this one. And let's go to this one right here. So here I've got, this is what I'm trying to build. I'm trying to build this equation down here. So I'm going to start one thing at a time. So first off, here I'm trying to build carbon. So I'm going to use the equation up here that talks about carbon. And that's the top one. But notice I wanted 2 moles of carbon. So I'm going to double this recipe. I'm going to multiply all the coefficients by 2. And so whatever I did over here, I have to do to this number. So since I multiplied all of these by 2, I'm also going to take this number and double it. Okay? So now, if I'm keeping track, I've got the carbon taken care of. Now I'm going to look, well, I want hydrogen. So I look at the equation up here that involves hydrogen, and I see it's the second one. And I don't need to change this at all because I want 1 mole of hydrogen on the left side of the arrow. And this equation has that. It has 1 mole of hydrogen on the left side. So I don't have to change this number at all. Then nextly, that's a new word. Then lastly, I want to get C2H2 on the right side of the reaction. So if I look up here, well, this talks about C2H2. It talks about 2 moles of it. I only want 1 mole. And I want it on the right side of the reaction. So what I'm going to do is I'm going to take this piece up here, I'm going to flip it, and I'm going to reduce it. I'm going to, halve it. Take it in half. So now all of these coefficients are going to get halved. So 4 becomes 2, 2 becomes 1. And notice these also have been flipped because I wanted this C2H2 on the right side of the arrow. So everything gets flipped. And so I flipped the sign. It was originally negative 2,598.8, but now I'm making it positive. And then I'm halving this number because I halved everything over here. And so if I look, I see carbon dioxide cancels out. I also see that I have 2.5 moles of oxygen here and 2.5 there. And so they cancel out, and the waters cancel out. And I'm left with this target reaction that I wanted. So notice this, the only thing that doesn't get crossed off is exactly what I wanted to end up with. And then the last thing I need to do is I needed to actually add these together. And I think I maybe forgot to do that on my slide. But I would just take negative 787 plus a negative 285.8 plus 1,299.4. And then I would have my final answer for enthalpy value. Okay, so that is Hess's law, how to use it, and how to apply it given these intermediate reactions.